Just like the stars they contain, galaxies evolve over time. They form and change through a wide range of processes. However, our understanding of galaxy evolution is still in its early stages. There's broad agreement about many of the major processes that shape galaxies, but the exact sequence of events that leads to a spiral or elliptical galaxy is still hotly debated. It may even be that the life history of one spiral is rather different from another one. In this chapter, rather than trying to develop a complete picture of how a galaxy evolves over time, we're going to try to focus on understanding the common processes that shape galaxies, including both ordinary galaxies like ours and some of the strangest ones we see.
We're going to start with some of the major types of observations of galaxy evolution and what this can tell us. Recent advances in observational technology are letting us see the earliest galaxies for the first time, filling in a lot of new information about how galaxies evolve. However, there are other observational clues to galaxy evolution that we've known about for decades. Next, we'll run through the important processes that shape a galaxy's evolution. All of these processes play a role in shaping a galaxy, though the size of that role varies tremendously from galaxy to galaxy. Finally, we'll look at some of the most extreme galaxies we see, the ones that host active galactic nuclei and quasars, and see what they can tell us about the early history of galaxies.
A galaxy is much more complex than a star. While a star is just hydrogen and helium gas with a few impurities, a galaxy is a mixture of stars, gas, dust, and as we'll see later, dark matter. Different parts of this mixture move in different ways in different parts of the galaxy. They often feed directly into each other, as we saw when we discussed the star-gas-star cycle a couple of chapters back. And galaxies can affect each other, something that only rarely happens with stars. So the evolution of a galaxy is much more complex than the evolution of a star. In fact, it's likely that any two galaxies will have very different histories, even if their starting conditions are very similar. There is no one variable, like mass, that we can use to determine the fate of a galaxy.
Nonetheless, there are many observational clues we can use to piece together the history of galaxies. These observations can be divided up into two major categories. The first comes from studying stellar populations and dynamics. This is a sort of forensic approach, looking at a modern galaxy to determine what happened to it in the past. The other approach is to simply look at galaxies at different times. Remember that as we look further into space, we're also looking further back in time, since light moves at a finite speed. Most galaxy formation occurred in the early universe, so if we want to see what a young galaxy looks like, the best way is to simply look at galaxies that are billions of light years away from us. Let's examine both of these approaches to studying galaxies in more detail. In the chapter on the Milky Way, we saw that the stars in our galaxy are divided into more metal-rich population 1 stars and metal-poor population 2 stars. This reflects the evolution of the interstellar medium these stars formed out of. The star-gas-star cycle enriches the ISM, so the more metals a star has, the younger it's likely to be. Hence, population 2 stars are generally older than population 1 stars. In spiral galaxies like the Milky Way, population 2 stars are mainly in the bulge and halo. This tells us that the bulge and halo probably formed first, with the population 1 stars in the disk forming later. Along with the bulges and halos of spiral galaxies, most elliptical galaxies are also dominated by population 2 stars. This suggests that these ellipticals formed with a burst of star formation early in their history, and that very little star formation has happened since. Stellar dynamics means the ways stars move in the galaxy. In spiral galaxies, most stars either orbit in nearly circular orbits close to the plane of the disk, or in highly elongated orbits in the halo or bulge. This is almost certainly telling us how the gas was moving when these stars formed. Disk stars form from clouds of gas that were in circular orbits in the disk, while bulge and halo stars form from gas that was falling inward towards the central bulge. However, within any given galaxy, there are often groups of stars that are clumped together in similar orbits, regardless of what the stars around them are doing. This is especially obvious in the halo, where these streams of stars are easier to study. This painting shows the paths of a couple of these streams in our galaxy. It's likely that star streams are the remnants of smaller galaxies that have collided with the larger galaxy and been torn up by its gravity. In this image, you can see a faint spiral of stars perpendicular to the plane of a galaxy. This is probably a fairly recent collision, perhaps as little as 100 million years old, since the stars haven't had time to spread out much yet.
This infrared image shows the galaxy Centaurus A. Centaurus A is an elliptical galaxy, which normally wouldn't have much gas and dust. However, in this case, we see a parallelogram-shaped band of dust cutting across the center of the galaxy. This dust and the stars that go with it appear to have been absorbed through a collision with a spiral galaxy several 100 million years ago. When we look at the largest elliptical galaxies, we often see many dense knots of stars, comparable in size to the bulge of a smaller galaxy. Large ellipticals like this are generally located at the centers of dense clusters of galaxies, so they're likely to have absorbed many of their smaller neighbors. These clumps of stars are probably the remnants of these former galaxies. In effect, we're seeing what giant elliptical galaxies like to eat.
When we look at galaxies around us today, we see very little sign that new galaxies are forming anywhere nearby, nor is there a lot of raw material around ready to turn into galaxies. Most galaxies appear to be more than 10 billion years old, close to the 13.8 billion year age of the universe. This suggests that most galaxy formation happened in the first few billion years of the universe's history. So if we want to see what younger galaxies look like, we need to look into the past. Remember that the speed of light is finite. It travels at 300,000 kilometers per second. We can also say that it moves at a speed of 1 light year per year. So it takes a year for a beam of light to travel a light year to us. And if we see something a light year away, we're seeing what it looked like a year ago. When we look at the star Betelgeuse, we're seeing it the way it looked 450 years ago, since it's 450 light years away from us. For most stars, 450 years isn't enough time to make a noticeable difference in how they look. But Betelgeuse is a red supergiant star that's near the end of its life. So there's a chance that it has already destroyed itself in a supernova explosion. But we won't know it until the light reaches us. When we look at the other large galaxies in the local group, we're looking a couple of million light years away. So we're seeing what they looked like a couple of million years ago. This is still a short time in the life of a galaxy.
If we want to see what galaxies looked like billions of years ago, we need to look at galaxies billions of light years away. Until recently, this hasn't been possible. However, new technology like adaptive optics and long-exposure space telescope images has allowed us to start seeing galaxies this far away. One clear trend we see as we look at galaxies 6 to 8 billion light years away is more active galaxies. In other words, there are many more galaxies with extremely bright objects in their cores. Later in this chapter, we'll look more closely at active galaxies and see what this implies about these galaxies and their evolution. In this ultra-deep field image from Hubble Space Telescope, we can see galaxies that are closer to 10 billion light years away. Here, most of the galaxies we observe are much smaller and more irregular than galaxies we see today.
Finally, there is one other important set of observations we can do on early galaxies. This is known as the Lyman alpha forest. Lyman alpha is the name given to a very strong hydrogen absorption line in the ultraviolet part of the spectrum. Whenever light passes through a cloud of hydrogen, the light at this wavelength is absorbed. If the light then travels through an expanding universe, the absorption lines are redshifted towards the visible part of the spectrum. When we look at the spectra of very distant galaxies, we often find large numbers of strong absorption lines at a series of wavelengths in the visible and ultraviolet parts of the spectrum. These come from clouds of hydrogen in the intergalactic medium, the space between the galaxies. The clouds lie between us and the galaxy we're observing. Each cloud produces its own Lyman alpha absorption, and then the absorption line is redshifted by an amount that depends on how far away the cloud is. The further the cloud, the more redshifted the line. From the amount of absorption, we can tell that these clouds are large, often galaxy-sized. There's a good chance that these are the sorts of clouds that galaxies form out of, and hence observing them gives us clues about galaxy formation.